Theoretical physicists do not study time travel to write science fiction. They use it as an extreme stress test. By designing mathematical time machines, physicists force the laws of the universe to their absolute breaking point to see exactly where they fail. The ultimate stress test involves something called a closed time-like curve. Within the framework of general relativity, this is a path through space and time that loops back on itself, allowing a particle, or an observer, to return to their own past. To understand how this works, we look at this animated diagram of a standard Minkowski light cone. In flat, empty space, the geometry of causality is strict. Your past is below you, your future is above you, and light dictates the absolute boundary between them. But space-time is not rigid. If you introduce a massive, rapidly rotating body, it drags the fabric of space-time along with it. Rotate it fast enough, and that dragging effect physically tilts the light cone along the direction of rotation. Tilt it far enough, and the future light cone intersects the past. The math is clear. The geometry of general relativity explicitly permits time travel. Theoretical physicist Kip Thorne used this exact mathematical permission slip to ask a highly specific question. What absolute constraints do the laws of physics place on an arbitrarily advanced civilization trying to build one of these machines? Stephen Hawking, however, provided a direct opposing hypothesis to Thorne's thought experiments. Hawking proposed the chronology protection conjecture. He asserted that the universe possesses an inherent physical mechanism that actively prevents the creation of macroscopic closed time-like curves, no matter how hard an advanced civilization tries. The core problem is that general relativity by itself does not enforce this protection. The geometry allows the curves to exist. Finding this chronology protection mechanism requires mapping the exact border where the laws of classical general relativity clash with the microscopic laws of quantum gravity. To understand how causality protects itself, we must systematically construct theoretical time machines, run the math, and hunt down the exact physical laws they break. The simplest way to build a closed time-like curve is to analyze a space-time where the time machine has eternally existed. Van Stockham's 1937 solution features a central cylinder of rapidly rotating dust. This rotation drags surrounding frames so violently that light cones tilt over circumferentially. Navigating this dashed path, an observer moves forward locally, but backwards in coordinate time, returning to the moment they departed. The math holds up, but the physics fails. For the frame dragging to be severe enough to tilt the light cones, the dust cylinder must be infinitely long. Because an infinitely long mass cannot exist, chronology protection survives its first test. A functional time machine must be finite in size. If an advanced civilization constructs a finite, localized time machine, they create a specific boundary in space where time travel begins. This is called a compactly generated chronology horizon. This diagram maps the boundary. The brim is the normal chronal region. The bowl is the future chronology horizon, where loops start. At the center is a light loop called a fountain. To form the boundary, light paths spiral outward from this fountain. For any finite time machine to activate, the laws of geometry dictate that these specific generators must be able to emerge from that fountain. For generators to physically peel away from the fountain, the geometry requires an optical effect. The bundle of traveling light rays must undergo a net defocusing. In general relativity, light does not bend itself. The focusing or defocusing of light is directly dictated by the density and type of mass and energy it passes through. This integral specifies the energy conditions required to force those light rays to defocus. The term T alpha beta represents the stress energy tensor, the total mass and fields. For rays to defocus, the total value of this equation must evaluate to less than 0. A negative result here means the system must violate the averaged null energy condition. All ordinary, familiar forms of matter satisfy this energy condition. Generating a negative result requires exotic matter containing negative energy. Classical geometry allows the Mexican hat topology to exist on paper, but the classical energy conditions forbid the matter required to actually build it. The machine shuts down before it can activate. Is it possible to bypass the fountain entirely and engineer a chronology horizon that avoids this energy violation? This maps a topological loophole called Misner space. By folding boundaries of moving space together, the horizon's generators are closed loops of light, rather than rays peeling off a central point. Because no light defocuses, Misner space satisfies the averaged null energy condition. But physics has a secondary trap. Hawking proved that the moment any actual mass or energy attempts to flow through a Misner horizon, it instantly triggers a violation of a stricter law, the local null energy condition. Even when exploiting obscure topological loopholes, the universe forces an energy violation the second you put a physical object through the loop. This chart reveals a systematic pattern of failure across every time machine attempted in general relativity. The eternal cylinder fails because it demands infinite mass. Contracting bodies fail because their fountains demand negative energy. And topological loopholes fail because introducing actual matter breaks local energy constraints. Hawking's chronology protection conjecture holds true, but it does not rely on a single isolated law against time travel. General relativity acts as a geometric canvas, willing to bend into infinite loops. It is the strict energy conditions of classical fields that act as the physical failsafe, blocking causality from collapsing. But classical physics is not the final word. We know classical matter forbids these curves, but we do not fully understand the behavior of quantum fields in highly curved spacetime. Chronology protection is an emergent property that points us exactly to where our current models break down. To know for certain if the universe protects time, we require the next great frontier, a unified theory of quantum gravity.